Now that we've completed how the muscle physiology works, we kind of need to get into how the body controls those muscles. And the first thing to discuss is looking at motor units. Now, a motor unit is going to be the motor neuron and all associated muscle fibers. Now, I'm saying all associated because this could be 4 or 5 fibers. This could be a couple hundred fibers. It varies based on the muscle. So one neuron, one motor neuron, to all of the muscle fibers is connected to. Now, this connecting to all the muscle fibers was causing all the muscle fibers to contract at once. So if that neuron fires, every muscle fiber that's attached to will then also contract together. And you can have, I mentioned, 4 to several hundred. It all depends on the amount of control that is needed for that muscle. Certain muscles in your body need more fine, precise control, while other muscles just need more general, basic control. So those small units give nice, precise control. Think about things that are in your face, your muscles of your eye, for example, or different facial muscles. They have a lot more control and a lot more functionality of how they work. You control them compared to a larger muscle of your leg, for example. Because the larger muscles, the larger motor units, are more weight-bearing. Things where you pretty much move one direction and that's it. Or think about your lips or your eyes, how many different directions your eyeball can move in when it starts focusing distance, near and far, left, right, up, down. So you need much more precise movement in the smaller motor units and more general control in the larger motor units. Now, these motor units, these muscle fibers, they are spread throughout the entire muscle. You don't have it where it goes to one side or the other side. It's intertwined, it's mixed. And the reason that's important is if you look at this one, you can see how this one particular one, the red, goes here, goes out here, goes over here, goes down. Why is that important? Why is that significant that we have it spreading out? Well, because if it only went to one side, only the side of that muscle might contract. So if you're only using a couple motor units, if they all were on the same side, that side would contract and be an uneven pull on that joint. But by spreading out, if you're only using a few, the fibers are spread across the entire muscle, providing an even pull for that muscle. So it's good to have them spread out. So if you're not using every muscle fiber in the muscle, they're still causing the entire muscle as a whole to contract, not just one half or one part. The term muscle twitch. Now I have the definition up here as brief contraction of all muscle fibers in a motor unit in response to single action potential in the motor unit. The basic gist of that is it's a quick contraction. A lot of times you might not even see a muscle twitch or be aware of it. It's the muscle just quickly, just a little tiny twitch. But that only happens if the threshold is met. Remember, we talked about greater potential to action potential. You had to hit that negative 55 millivolt threshold. So as long as the signal was strong enough to hit threshold, it moved down to the muscle, creating the twitch. So we have this muscle twitch, the movement. Now you can record these. If you ever had a myogram, for example, maybe it's just electrodes hooked up to your arm or a leg or someplace, or even could be anywhere in the body. What that's doing is it's measuring the electrical impulse as it travels through your muscle. And you can show then if there's small or large impulses. What I mean by that is, it's not that the action potential is different. It means how many action potentials, the frequency, or how strong the muscle is because they're all firing together versus only one motor unit or two motor units. So a myogram can show the electrical stimulus inside the muscle. Here's a single muscle twitch, and it's showing the myogram of a single muscle twitch. You have the initial phase in yellow over here. That initial phase, if you notice, hasn't generated any tension. It's flat. the tension hasn't started to increase yet. That's because the latent phase is the period from stimulation until the initial contraction. When you're saying, hold on, stimulation and contraction, what is that? That would be the electrical signal coming from your brain, your spinal cord, so that action potential. It's then going to the neuromuscular junction, converting through the neuromuscular junction, then it's traveling down the sarcolemma, so action potential, propagation, or conduction. It's going down the T-tubule. It's getting the calcium into troponin pulling out of the way, and then tropomyosin moving out of the way, allowing myosin actin to bind. That whole entire thing is your initial latent period. So lots going on there, but the muscle hasn't moved. The period of contraction, that's this set right here. You can see how the tension's going up. You're increasing tension towards the top. That increase in tension is the myosin going through the cross-bridge cycling process. It's moving the thin filaments towards the center. The muscle is shortening. That's the contraction period. Calcium has flooded the muscle to allow troponin and tropomyosin out of the way. And then you have this relaxation period, this whole large slope heading down. The muscle is going back to its resting state. At this point, calcium is an active process of being pumped back in to the terminal cisternae, and troponin and tropomyosin are going back over and covering. Notice it takes more time. It's very fast for everything to go pouring out down its diffusion gradients. But it takes more time to put everything back and reset. So the period of relaxation, on average, will be a little bit longer than the period of contraction, because it's taking time to reset everything, put everything back together. So latent, then you have the period of contraction, then you have the period of relaxation. And that works out pretty much for every muscle. Now here we have the individual twitches of 3 different muscles of the body. This first one over here, if you notice, the one that's dark blue, that's really quick up and down. That's because that is going to be the lateral rectus muscle of your eye. Think about your eye. How it seems to be instantaneous. You can focus on different spots, different places. That's because it's very precise and a very fast response, a very fast twitch. But the other two, you get into gastrocnemius, takes a little more time, then soleus takes a long time to go through. That's because those 2 muscles are both found in your calf. Gastrocnemius is what is basically looks at the calf, while soleus is deeper. They're helping more with weight bearing, and therefore they are a little bit slower to respond, a little slower to act. Now, it's not saying the muscles are slow, but compared to the rectus muscle of the eye, that lateral rectus, it is slow in comparison. Because the time from the bottom is milliseconds. Not seconds, milliseconds. Lateral rectus contracts and relaxes in 20 milliseconds. Soleus, 200 milliseconds. So again, the larger, more weight-bearing, slower to contract, slower to relax. Because they're also basically utilizing more force, more energy, not quite the same as your eye muscles. But all this muscle contraction, muscle twitch, it comes down to how the muscle generates tension. Now I have up here about this all or none phenomenon. I already kind of mentioned that action is going to occur when you have a stimulus coming in to a particular motor unit. But now every fiber in that motor unit will contract, but they always contract at the same strength. So not just all contracting, but all contract at the same strength. So when this particular motor unit A fires, it always generates the same amount of tension. Motor unit B fires, same amount of tension. So you can't make the individual fibers having different tensions here. That's based on more along the lines of how many motor units are recruited. The more motor units, the more tension will be generated. So you can't say it contracts partially. either that muscle fiber contracts or it doesn't contract. So a motor unit fires, every muscle fiber attached to that motor unit will also fire at the same strength. They all contract. There's no half or partial. Was it a strong or weak signal? Just either contract or not. Think on, off, done. That's it, on, off. So the muscle tension can vary based on the entire muscle, not the motor unit. So that's why I have up here whole muscle. Your muscle obviously can have different amounts of tension, different amounts of force. Are you picking up a small pencil? Or are you picking up a 20-pound weight? Or trying to move a 50-pound sack of something? The idea is the muscle itself will have different amounts of tension based on the frequency of stimulation and the strength of the stimulus. Frequency is how fast the action potentials are received. Strength of stimulus is basically say, okay, usually when you do an action potential, the faster the stimuli, the harder or stronger the impulse is. So if we take a look at this, here's an example of the actual stimuli occurring more frequently. Looking at this one being summation. Incomplete tetanus. You can follow it. It goes up, relax, up, relax, up, relax, up, and finally relaxes. But that is going to be incomplete tetanus, where you contract, start to relax, but don't come all the way back down. Contract again, start to relax, contract again, start to relax, and just keep on going. Everyone becomes a little bit stronger because you never fully relaxed the first time. So it builds in tension. The other one here is going to be complete tetanus. So if you were to contract and just hold, because you have that initial stimulus and then just flatlines. There's no rest, there's no relaxation, that's it. So we have this incomplete and complete tetanus. You're kind of building up your muscles. And this brings us to the idea of threshold for a second time. This threshold is not exactly the same as what we've been talking about in the past. We've been talking about threshold with electrical stimuli. So for example, resting membrane was negative 70 millivolts. If you hit negative 55, you hit threshold. It was a certain point, certain millivolts. This threshold is still a certain point you have to hit, but we're looking at tension now, looking at signal strength. It's a little bit different than that one. So it's still a floor you have to hit, but it's using different mechanisms to get there. So as long as you can go above threshold for the muscle stimulus, that means you've generated enough force to show a movement. Because when those muscle fibers first start to contract, all they're doing is getting the tension generated. They have to move a certain amount before the muscle finally moves. The initial part is kind of the getting ready, then you keep going and cause the movement. The force contraction, as we mentioned, is based on multiple motor units added together. One single motor unit might not even be able to move a large muscle. Depends on the muscle, of course. But as you have this second, and third, and fourth, and fifth, and all these motor units are adding together, that's where the force of the muscle really comes from. So we take a look at this. You'll notice that in the bottom part of this graph, right here, we have no movement until there's a little blip at the end there. But if you notice up top, we have stimuli. The reason being, those stimuli did not reach the threshold mark. They weren't strong enough. So what we have going on here now is, number 3 here, that one is the first one to reach threshold. And if you notice, it reaches threshold, and we end up with 2 muscle fibers. So 2 more units, creating a very weak signal. But then as you keep going, notice they get further and further and further past threshold. The signal each gets stronger and stronger. Now, I drew up there and stopped there because these ones aren't going to make a difference. We'll get to that in a second why. But if we're looking at this grouping right here, going from threshold up to a maximal contraction. Those correspond to this section right here. You'll notice that each time you have an increase of motor units, more and more, until they're maxed out. That corresponds down below to these different parts. Notice each time you have higher and higher and higher tension. That's because as you increase the stimulus strength, the top part, you increase motor unit recruitment, which means you bring in more motor units, more muscle fibers. More muscle fibers means more force or more tension is generated. But that only works until your maximal force. These top three, if you notice, didn't increase. The stimulus got stronger and stronger, but you couldn't generate any more of these motor units. You already maxed it out. There's no more motor units to recruit. Therefore, you couldn't end up with a higher and higher contraction. There's nowhere to go. So we have this kind of lower and upper limit. Threshold in the bottom, you have to have enough stimulus to reach threshold to generate the movement. But then you can also have a maximum up top, where even if you go past that maximum, you can't generate more force, more tension. There's just no more muscle fibers. So it's based on the amount of stimulus coming in to cause the muscle contraction. But we have an interesting side note on that. There's something called the treppe effect, or treppe, the staircase. What's happening is you have an increased contraction in response to the multiple stimuli of the same strength. So same stimuli, but getting stronger and stronger. This is usually what happens during your warm-up period. You're always supposed to stretch and warm up before you exercise, or stretch and warm up before you play a sport. But why? Think about when you first start to warm up. Maybe you jog a little bit. And you start on jog and it's like, all right, I'm just getting going. But then about 10 minutes later, hey, you're moving and everything feels a little better, a little bit faster. You're moving a little freer. The step is a little bit livelier. That's because as you're warming up, your muscles are getting ready to work. This initial phase, this initial warm-up, getting ready phase, is because you're increasing calcium in your muscles. Remember back to physiology. We said that the terminal cisternae released calcium into the muscle cells. That calcium allows troponin to change shape. Well, by having plenty of calcium always present, it keeps that shape changed, keeps the binding sites opened, and makes it easier for myosin to bind, creating tension. Secondly, besides this calcium, enzymes become more efficient. As your body gets warmed up, the physical muscles become warmer. As the muscles become warmer, the enzymes become more efficient. Because as the body increases in temperature, enzyme activity becomes at a higher state, or say moves to a higher state. So they're more efficient and everything runs a little bit smoother. So between the enzymes and the increased calcium, your muscles are ready to go much more efficiently than they were before you warmed up. So that's why maybe 10, 20 minutes in onto an exercise or workout, you just all of a sudden feel like you're hitting your stride, really getting going. Because the muscles are finally at the point they have the full amounts of calcium. The enzymes are working efficiently. They're warmed up enough. They're good to go. I mean, think about any professional athlete. They all have their own warm-up routines. Some start a half hour out, some start an hour out. Some start 2 or 3 hours out. They've all learned what their bodies need to get warmed up and efficient, so this is ready to go at that first play of the game. So your body, getting yourself ready to go, getting moving, so you're off and moving efficiently. So basically what's happening here is each time the tension gets a little bit higher, you're creating this upward curve. Each time you notice it comes down to zero, you fully reset between. So this isn't incomplete tetanus. You're not building on the previous one. It's coming all the way to rest, starting all the way to rest each time. So treppe, the muscles are warming up. So a little bit about how the muscles work. From treppe muscles working to tetanus, incomplete and complete, dealing with the motor units and their recruitment from one motor unit to many to increase the tension of the muscle.